And I'm going to talk about fabricating capacitive pressure sensors using a ferrofluid sacrificial layer. So one of the research themes of my group is fabricating MEMS with non-standard materials and techniques, which basically means not silicon. So I'll be talking a little bit about how people typically fabricate capacitive pressure sensors. And why, in my group, we wanted to fabricate a sensor on stainless steel, and why ferrofluid as a sacrificial material helped do that. Then I'll discuss the actual sensor we made itself and its fabrication and some of the test results. Okay, so I apologize for the lack of pictures on the first couple slides. Typically, when you're fabricating a capacitive pressure sensor, you want a thin membrane that's suspended above a hermetically sealed chamber so that when you apply an external pressure, the membrane deflects into the chamber and you'll get a change in capacitance if your membrane and substrate are both conductive. There are two standard techniques for making these structures. One at the bottom is direct bonding, where your membrane comes from one silicon wafer and your substrate is another wafer, say glass or silicon, and you bond them together using either high heat and pressure or eutectic bonding or some sort of adhesive bond. And in all these methods, what's critical is that your substrates are very flat. So silicon wafers and glass substrates you'll find typically have surface roughness, say less than 10 nanometers. And that's what you need to get good bonding over the entire area. So that's the direct bonding method. And in the case of surface micromachining, you only need one flat substrate, but you'll use typically many photolithographic steps to create a sacrificial layer of either photoresist or SiO2, and the membrane over top of that, and then you'll release with either a wet etch or a dry etch afterwards. And this also can have some higher temperature steps, because there's usually PECVD deposition of membranes, and sometimes the sacrificial layer itself is also a chemical vapor deposition. In our group, we had a project that for sensing blood pressure inside a coronary stent, which was made of stainless steel. And one of the initial attempts at fabricating a system that would do that was to fabricate a pressure sensor with stainless steel as a substrate so that it could be welded directly to the stent and form a permanent bond that could last inside the body for many years. And so this was sort of the motivation for doing this. And so because stainless steel is rougher than silicon and also has a much higher thermal expansion, we wanted a process that could work at lower temperatures and on a rougher surface. And this was one of the attempts that a student in our lab tried, was trying ferrofluid as a sacrificial layer. I'll show the fabrication process in the next slide. But the benefits of this, as I mentioned, are that it occurs at room temperature, and there were also no photolithography steps in this particular process. So in this case, it was time saving as well. So this is the particular device, and as you can see, the substrate is stainless steel. The lateral dimensions are 1 millimeter by 1 millimeter, and the cavity depth itself was 10 microns. And there are some holes in the corners to increase the volume inside. The reason being is that when you apply an external pressure and bend the membrane, it's really the pressure inside equalizing to the external pressure that prevents further deflection of the membrane in this case. So if you increase the internal volume, you allow more deflection of the membrane and a better sensitivity of the device. And the materials used were 304 stainless steel. It says 316 here, but actually for the devices shown in this, it's 304. And then there is a Parylene layer in blue, which forms the dielectric of the capacitor. And then the top electrode is titanium that was e-beam deposited. Just quickly about ferrofluids, because they're not familiar to most. A ferrofluid, they're commercially available, and they consist of paramagnetic nanoparticles, say 10 nanometers in diameter, that are suspended in some type of carrier fluid. The picture on the top right there shows a fluid on a surface with a permanent magnet placed underneath. You can see that it has this interesting phenomenon. It's called spiking that occurs when you place a magnet in its proximity. And generally the property is that the fluid flows towards where the magnetic field is strongest. So in our particular fabrication pressure, we needed a ferrofluid sacrificial layer that would survive inside a vacuum, as we do processes in the vacuum, in particular inside a chemical vapor deposition of Parylene, which occurs at 1.3 pascals. So we chose a ferrofluid indicated at the bottom there with a very low vapor pressure, which is not affected by a vacuum environment. Here is the schematic of the fabrication process. It begins with electro discharge machining of the stainless steel substrate. So if you're not familiar, this is not widely used technique, but it essentially takes a tungsten needle and applies a negative voltage to it as you apply a positive voltage to some conductive material you want to machine. And when you bring the needle in proximity to the substrate, you can remove material from it, and it's quite good at getting good depth control. It's used in prototyping of certain very niche applications, but we have one in our lab, so that's what we used for this. Then there was depositing of ferrofluid inside the cavity that allowed for deposition of the membrane over top. The chemical vapor deposition of the Parylene, followed by the E-beam deposition of titanium. Then the epoxy was removed from the bottom, and a permanent magnet was used to essentially draw out almost all of the ferrofluid. Actually, in this case, because we used 304 stainless steel, which was magnetic material, some of the ferrofluid remained inside the cavity, and we believe that the reason for this was that the substrate itself was also magnetic. So there was actually mostly air, but also a small amount of ferrofluid remaining. So that picture is not entirely accurate. And then to seal the cavity afterwards, epoxy was used again to form the hermetic seal. So this is what the EDM chip on the top left looked like before any of the other steps. This sort of granular appearance in the center is from the EDMing. The stainless steel itself has, say, a surface roughness of many hundred nanometers. Then the picture on the top right is the Parylene coating after the ferrofluid is deposited, and then titanium E-beam deposited on top. And the final sensor itself is shown in the bottom left. So there were many sensors fabricated this way. And characteristic of all of them was that when the ferrofluid was removed with the permanent magnet, as often occurs in MEMS, where you have a fluid involved, it tends to draw the membrane towards the substrate because of the adhesion between the fluid and the materials itself. So actually what happened in this case is that the cavity was 10 microns deep, but the optical profile of the top surface showed that the membrane was depressed to about 6 microns with relatively good flatness considering the roughness of the substrate. And so what's really going on there is there's a small amount of ferrofluid at the very bottom, which is making up the difference between the 6 microns and the 10 microns. And to get better control of this, we really need a better apparatus for, say, depositing the ferrofluid inside the cavity. Now, whether this is actually a benefit or a drawback requires more characterization, but probably because of this remaining ferrofluid, the response to the sensor was actually linear with pressure. What's characteristic of capacitive pressure sensors is that when the membrane touches the bottom of the cavity, the increase in capacitance with pressure is linear. So this could probably use some modeling as well, but that's the experimental result that we found. And the response of, say, 0.4 picofarads with about 32 kilopascals, which is about a third of atmospheric pressure, is comparable to what you'd find in a silicon-based capacitive pressure sensor that you could buy commercially. And then the final slide is indicative of one difficulty with this sensor, which is that it was highly temperature dependent. So its base capacitance varied quite strongly with temperature. The primary reason for this is that the dielectric we use is Parylene-C, which has a high dependence of dielectric constant on temperature. So in our biomedical application, there's a fairly narrow temperature range, but this is not good enough. So one idea is to use Parylene-N, which is a much lower dependence on temperature. Maybe there are other things we can think of to reduce this kind of dependence and just isolate the pressure dependence of the sensor itself. So in conclusion, 4 minutes left. Well, okay. In conclusion, ferrofluid was used as a sacrificial material in a surface micromachining type fabrication process, and the sensors worked and showed a linear response with pressure, indicated there. The membranes showed relatively good flatness of 1 to 2 microns over a lateral dimension of 1 millimeter, especially considering the roughness of the substrate was on the order of hundreds of nanometers. No photolithographic steps were necessary in the fabrication process. And potentially, given a suitable application, this might be applicable. It doesn't necessarily require the use of stainless steel, for instance, or microelectrode discharge machining. It just requires the right circumstance. So it's of possible applicability to fabrication of other MEMS devices. And I am in the Takahata lab again, and these are the sources of funding. And that is the end of the presentation. So if anybody has any questions, please ask.